The main results so far, we have a partition function that we have to calculate. This part was the Gaussian model. Now we are modifying it by adding a quartic term, and the quartic term is just the Fourier transform of this term that we add to the Gaussian model, 4 spins, and each spin has been Fourier transformed. So if you put this into the sum, you will well, I should write this as an integral. If you put this into here, you will have 4 integrations over different momenta and one sum over n. So this sum over n will introduce a delta function, and the 4 momentum integrals will become 3 momentum integrals. Okay, so this is what we did last time, and as I said, what we are going to do is we are going to do for this model what we did for the Gaussian model, namely integrate out half the momenta spins. So I divide it into 2 parts. So the sigma 1s are the ones we are going to integrate out. So you can write sigma q is this plus this, integrate out sigma 1. Okay, so I will just write that expression. So what are we calculating here? So we are doing this integral d sigma 1, so that is this guy, of the full effective action, which I will write. So this part I call as the HF free, this part is the interaction one. Okay. So we will have the free part. Remember, the free part splits into 2, HF sigma 0 and HF sigma 1. There is no connection between the two, so I can write that here. So this I will write as HF sigma 1, and this is not being integrated, so I will write that here. So this whole thing is z, and then I have to this guy. So this is HI. This doesn't. This has quartic pieces. So this is the integral we have to do. Okay, this is where we stopped last time. And what I want to do today is to work this out. So what I will do is I will give you the general rules and work out, outline the calculation. I will work out a few sample examples and then write down the complete result. So what is the procedure or method? Well, first of all, we have to expand this. So this has a well, so let me write it this way before we do that. So expand one minus HI plus. So that is a perturbation expansion. So it is assumed that this H interaction has a small parameter in front of it. You expand and evaluate each of these terms in here. So we have to evaluate this expansion. So 1 minus HI plus half, oh this is squared, sorry, where this means do this integral. Whatever operator is there. Okay. This object is a Gaussian, it is just this. So you just have to do Gaussian integrals. So these are Gaussian integrals. What are the typical terms that will occur here? HI will have terms like this. So there will be some number of sigma 1s, some number of sigma 0s. So typically the sigma 0s are not being integrated, they just multiplied, and so typically you will have things like sigma q1, sigma 1 q1, sigma 1 q2, things like that. Okay. And the way to do Gaussian integrals you are familiar with, or if you have done field theory you know it directly, is when you have many of these sigma 1 q3, sigma 1 q4, you combine them in pairs. These are the so called weak contractions. Combine them in pairs and replace each pair by what is called the propagator, which you can derive from this, and the propagator is is 2 pi to the power of d. So in this case q1 plus q2 by, so replace this by that, replace this by that, the corresponding ones, and but you have to make all possible contractions. So this could contract with that, this could contract with that, and so on, and each contraction you replace by that, and this is best done diagrammatically. Okay. After you, okay, so we are going to do that, but after you do that, after you have done these integrals, what are you going to get? You are going to get something which we will call, so since all the sigma 1 integrals have been done, you only have sigma zeros left. So whatever you get you will write as e to the power of minus h some prime sigma 0, okay, and whatever you get is the new Hamiltonian in terms of sigma naught, where now the momentum is this range. Okay, so this is the steps we have to do, except finally after obtaining something like this we will have to do some rescaling. So write, so final call it h prime has to be in this form, where the sigma naught prime is some scaling of q times sigma naught of q. It is some scaled version of this. Oh, I should put it the other way around, sorry. So you replace your sigma by some rescaled version, call it sigma prime with q prime, where q prime and q prime is just 2q. This is exactly what we did in the Gaussian case, and we will do the same thing here. And we are going to choose this C so that the first term in this has this form. Okay. So final h naught has to have the form u prime, which could be a function of the momenta. I will just leave it like that, u prime integral over q1 prime, q2 prime, where all of them range from 0 to 1 because the range has been doubled. Okay. Similarly here. So this, we have to do this integral, put your final answer in this form through this rescaling, and this C will be chosen so that the first term in this is precisely q squared with the coefficient half. That is the goal. This is what we have to do through doing these integrations, and then we will get an expression for u prime and r prime in terms of u and r. Okay. So get u prime r prime in terms of u and r. So this is what we have to implement. So first we have to do the integrals, then we have to do that rescaling and put it in a canonical form. Okay, is this clear? I hope. So what I will do is I will work out some of the examples. So let's first of all see what this has. One is trivial, there is nothing to do because it is just a Gaussian integral and you will get some number. So I will write that. I should mention one more point, after you evaluated this, you see this is, we want to write it as an exponential of, we want to write it in an exponential form. So the rule is, when you evaluate this, you evaluate only the connected graphs, connected terms. Okay? If you evaluate only the connected parts in this, that's precisely what goes into the exponent. Okay? So in other words, if you calculate all the connected parts and put it in there, you bring it down in various powers, that will reproduce the rest of the disconnected parts. So that's something you know from properties of the generating function, but you can explicitly prove it using combinatorics. So I will say here connected. So what do I mean by connected parts? If you have 4 sigmas all at one point, then this is a connected part. So in other words, if you have, so this is a typical graph, sigma 1, sigma 1, sigma 1, sigma 1, and let's say another sigma 1, sigma 1, sigma 1, sigma 1. If these are all contracted amongst themselves, then this is disconnected, so you don't calculate this. So you only calculate graphs that look like this, for instance, with at least one connection between them. Okay? That's what goes into this. These graphs you calculate and then put them into the exponent, and you're done. That's combinatoric fact. So okay, so the first term is this 1. 1 is just a Gaussian integral for that. Will just give you some number. Okay, the number has not much significance. It's some you can think of it as some constant ground state energy, which is no dynamics. It's independent of sigma naught. So we are left with this one, and then we left with that one. And then of course there's higher order, but we will concentrate on this. So let's do HI. So what does HI consist of? It's this, where I put sigma naught plus sigma 1 into that. So schematically, you have something like this: sigma naught plus sigma 1 Q1, Q2, and so on, minus Q1 minus Q plus Q2 plus Q3. So the 4 of these. So this will have terms involving sigma naught to the power of 4 plus 4 sigma naught cubed sigma 1 plus 6 sigma naught squared sigma 1 squared plus 4 sigma naught sigma 1 cubed plus sigma 1 to the power of 4. So these are the 4 terms that go, all of them inside the exponent. So you can put, where I'm being schematic here, sigma naught to the power of 4 is sigma naught q1, sigma naught q2, etc., etc. As we said before yesterday, this expectation value of sigma 1 is going to give you 0, as is this, because of symmetry. Odd powers will just give 0. So we are left with this, this, and that. So you can drop that. Again, this is just a constant, so it doesn't do much. So this sigma naught 4 is just a constant. So it just contributes directly to that. The non-trivial calculation has to be done here and here. So let's calculate that. So 6 times sigma naught squared times sigma 1 squared. So let me write this out fully in momentum space. So what is this? So this is something like this: 6 times q1, q2, q3, sigma naught q1, sigma naught q2, sigma 1 q3, sigma 1 minus q1 plus q2 plus q3. And there's a u here. These are 3 integrals. And we have to evaluate this. Okay. And what's the rule? Contract 2 of them with this. So what do you get when you, so in this, these are the 2 ones that you have to contract. So you'll get 2 pi to the power of d times the delta function involving q3 plus that. When you add q3 to that, you just get q1 plus q2. So this will be delta function of q1 plus q2. This is a d-dimensional delta function q1 plus q2 by q3 squared plus r okay. So this delta function makes q1 equal to minus q2. So that comes out, so you get 6u times integral q1 sigma naught q1 sigma naught minus q1, that's this. Then you have to do the q3 integral, so you get q3 by 1 by q3 squared plus r. So this 2 pi to the power of d, so remember each of these integrals, what are these integrals? These are d dq by 2 pi to the power of d. So when you do the q2 integral here, there is a 1 over 2 pi to the power of d which cancels this 2 pi to the power of d, okay. So that is why there is no 2 pi's here. So this is d dq by q1 by 2 pi to the power of d times that. So this 2 pi and this 2 pi cancel and get this, and you are left with this guy which goes there, and this integral I will write it out explicitly, it is d dq3 by 2 pi to the power of d. So here also it is I will write this explicitly, this is d dq1, what we are calling q1 is that. So q1 integral. So this term is the sigma naught term which is like this, which looks like this, and its coefficient is what you have to evaluate. That is an integral that you have to do. So the coefficient, the contribution of this term to the quadratic part is this, okay. Notice that it is just a constant, this is also going to be a constant, just a number. There is no q squared here, okay, there is no q squared. So if you look at this expression, that term is contributing to this r, it is not correcting this q squared, okay, so it is a constant. We will work out this integral later, so let us leave it like that. By the way, I should say the range of integration. What is the range of integration here? This is 0 less than q1 less than half, and here it is 0 less than half less than q3 less than 1, that is the range, it is not the full range. So this is all before the rescaling, at some point you will have to rescale, okay. So that is this term, so we have done that. So if you want to do hi now, we are left with this one. So is this clear? This is what in field theory you call the mass correction. Now what about sigma 1 to the power of 4, what will it give you? Sigma 1 to the power of 4 has 4 sigmas and no sigma naughts, okay. So as far as your final Hamiltonian is concerned, it has no sigma naught, it is just a constant. So in fact graphically this is the graph, sigma 1, sigma 1, sigma 1, sigma 1, 4 sigmas, and you just contract two of them, there is no sigma naughts, you just get a number. So we can write expectation value of sigma 1 to the power of 4 is some number which we are not interested in, so we won't even bother to calculate it. So we are done with the first term, okay. The only effect of the first term is to get a term of the form some constant times sigma q sigma minus q, where the constant we have to evaluate, but we know there is this factor of 6 and there is u, so it is proportional to that, and then whatever you get from this integral. Okay, so now let us do the more interesting one, well, which is hi squared. So this we will do graphically because I do not want to write out everything. So the idea is there are each vertex you can draw as a graph like that with u, and depending on the number of sigmas in it, you get different answers. So if you have let us say a term of this type, you will write it like this: sigma naught, sigma naught, sigma 1, sigma 1, and there will be 6 of these, and then there will be a graph with all sigma 1s. There will also be graphs like this and that. So there will be graphs like this, say sigma naught, sigma naught, sigma naught, sigma 1, 4, and there will be graphs with sigma naught, sigma 1, sigma 1, sigma 1. For these, have I got them all? Then I need one with all sigma naughts, and of course there is one with all sigma naughts. So these are the various things that come out of each of these HIs, and we have to put 2 of these together and get results. So now we are doing second order. So this is second order in U. Okay. So second order in U means there will be 2 of these, and you have to put them together. So one graph that you can have is this one. The sigma naught, sigma naught, sigma 1, sigma 1. You can contract that. Another graph you can have is this. Where you take this one, you take 2 of these, 1 sigma naught and 3 sigma 1s, and connect them. So there will be a u here, and a u here, a u here, and a u here. This will be a correction to the sigma naught squared term. This will be a correction to the sigma naught to the power of 4 term. Okay. So this will correct u. We won't worry about this graph because we already have one correction to R, to linear order in U. So this is order U squared, so it's much smaller than that. So we'll neglect this because it's order U squared. Okay. But we don't have any correction to sigma naught fourth so far. So this is the first graph that contributes to that. So we have to calculate this. So we'll evaluate this one. And what I'll do is I'll just write this out. So maybe I'll do it here. This one. So this comes from this vertex. Yeah. Connect these 3 sigmas. By the way, there is also a graph which is of this type. So there's sigma naught, sigma naught, sigma naught, sigma 1. Okay, and I can connect these. So this will give me sigma naught to the power of 6. Sigma naught. So this is a term. This is a term in the Hamiltonian which we didn't have before. It's a new term. Okay. So the recursion produces terms that you didn't have before. It's a new term. But later on we'll see that this graph, this term is unimportant for the purposes of it at hand. Okay. So we will only need the quartic and the quadratic teams. It will be necessary for some purposes, but to obtain a relation between R and U, R prime, U prime, this is not necessary because this is a different kind of graph. But it will play a role, later on we will see that this will play a role in actually if you do an exact calculation, you have to keep all these terms. Okay, in this approximate calculation we don't need that. So let me erase this. erase this. Oh, I'll erase this. This is a so let me draw this graph, put some momentum labels. So I'll call this Q1, Q2. I'll call this momentum P. So this momentum, if this is Q1 going in, Q2 going in, P going in, then this must be Q1 plus Q2 plus P by conservation of momentum. And then this we can call Q3, and then this will be minus Q1 minus Q2 minus Q3. So there is one undetermined momentum P. Okay. So and external vertices, things are all sigma naughts. So what are we going to get? So you're going to get sigma naught Q1, sigma naught Q2, sigma naught Q3, sigma naught minus Q1 plus Q2 plus Q3. That's just all these. And then you have two propagators. Remember the rule is contract sigma 1s with the propagator. So you will get some 1 over P squared plus R and 1 over Q1 plus Q2 plus P squared plus R. Okay. And this P is not fixed, so you will have an integral over all P. So I'm not working out explicitly all the contractions and all the momentum integrals, but you can see from your experience in field theory that's what's going to happen. All the undetermined momenta that are not fixed by the delta function constraints will get integrated over, and you'll get a graph like this. And there'll be a u naught here and a u naught here. So there'll be u squared. How many graphs are there like this? So you have to see how many ways you can connect these two. Okay. So if you just start with this graph, there's a 1 over 2 factorial from this. Okay. So there's a 1 over 2 factorial. Then there are you have to put two legs for sigma 1s out of the 4. So there's 4 C2s ways of picking this sigma 1s and 2 ways of picking that sigma 1, and then you can contract this with that or this with that. So it's that. Okay. So what is this? This 4 C2 is 4 6. So this is 36. Okay. So there's contribution of 36 to this. But actually, when you have external momenta, you have to maintain their identity, and these 36 will be divided into 3 sets of 12 each, where the 3 sets correspond to the 3 ways you can organize momenta. So in other words, you can have things like this: Q1, Q2, like that, Q3, Q4, or this Q1 can contract with Q3, Q1, Q3, Q2, Q4, or you can contract the Q1 with the Q4 and write Q2, Q3. See, there are 3 ways of organizing the momenta, and basically there will be 12. So between the 3 of them you will end up with 36, so there will be 12 for each. Okay. So there will be so each of these graphs will actually have a factor of 12, and then you permute the momentum and get 3 more terms. So I'll write this as in 12 into this plus 2 permutations. Okay, for one for this, one for this, one for this. Each one will have, there will be 12 terms. I think that is it. So this will be your, this is the calculation you do. So we have 2 calculations we have 2 integrals to do. One is this, one is this. Okay. Is this clear so far? So what I'm going to do now is I'll just summarize this by writing down some Feynman rules, which applied will give you these graphs. Then I'll write down the result. So let me write down the Feynman rules here. So basically, so first of all, you need a convention, label momenta, say ingoing. So you have to have some convention. So I'm having the rule, let's say that all momenta will be written as ingoing. If it's positive, it will be ingoing, negative means it's outgoing. So it's, okay, so ingoing. Rule number 2, the internal momenta. So when you integrate over this, what is the range of these momenta? Both P1 and P and this have to be less than, sorry, half is less than P is less than 1. This is in the range half to 1. This is also in the range half to 1. Okay, so this is also half less than, this whole thing is less than 1, half less than, both momenta have to satisfy that criterion, because any internal line that you're integrating over is in that momentum range. So it's not easy to do that constraint exactly, so we're going to do it approximately. Internal momenta have to lie in the range half less than q less than 1, and external momenta have to lie in 0 less than q less than half. So all these ones will be in the range 0 to half. Okay. Third, associate a factor 2 pi to the power of d delta function d q1 plus q2 by. So this is when you contract a line with q1 and q2, that put that as your propagator. 4, there is a factor of u times 2 pi to the power of d times delta function q1 plus q2 plus q3 plus q4 at each vertex. So at this vertex, a priori, if these are the 4 momenta, you have a factor like that. Okay. So when I write down this expression, all those delta function integrals I've done. So it's the result. And this is 4. Then 5th rule, we do a rescaling sigma naught, which I haven't done yet. Sigma naught q I will write as c times sigma prime q prime, where q prime is 2q. So here I am going to do a rescaling. After doing this integral, I will do a rescaling like this, and then integrate over all undetermined all momenta, because you have all momenta. So that will amount to, after you use the delta functions, that will amount to doing integration over the undetermined momenta. So integrate over all momenta, where this is a range of integration. So let's work out the result. I'll write down the result now. So let me do that rescaling here. So let's do that rescaling I just said. So I'm going to call this. So this is. So let me do it here, so not to confuse. So in this expression, I'm going to rescale. So sigma naught will be replaced by what? This guy, right? So I'll write this as sigma naught prime. Now what is q prime? I'm going to call it q1 prime. So q1 is q1 prime by 2. Okay. So we'll what have I called it? So anyway, q1 prime and there are 4 factors of zeta because there is 4, but all these integrals were integrals over q. Where is it? These are all integrals over q, but I want to write it as integrals over q1, q prime. So I get a factor of, each one gives me a factor of 2 to the power of minus d. Okay, so you get 2 to the power of how many integrals are there? So what should be here? See, you're replacing d q1 by right. So each one gives me a 2 to the power of d in the denominator, and I have 3 of these, so I get 2 to the power of minus 3d. Okay. And I'm going to write the final answer in terms of q1 prime, q2 prime. So I will call this as q1 prime by 2, q2 prime by 2, right. q1 is just q1 prime by 2. So because I want, after doing the integral, I want the final answer in terms of q1 prime, because that's my new argument. So I just replace my q1 by q1 prime by 2, and here, so effectively this q1 is just q1 prime by 2, this is q2 prime by 2, and so on. So this is q1 prime by 2. That's just changing names, because q prime by 2 is q. So this way, whatever, after you've done the result, you'll get your answer everything in terms of the primed q's rather than the unprimed q's. So the final answer, and what is this a correction to? This is a correction to our u. So let's write down our u corrected. First, there's our starting contribution, which was u. This is the original. So this is going into the exponent, and it's correcting the sigma 4th term, sigma naught 4th term. Sigma naught 4th term already has a term which you started out with, the original Hamiltonian, and then there's this correction. This rescaling is there for every term. It's just from these integrals and this, the fact that there are 4 sigmas. So every term will have this rescaling factor. What is the correction to this? The correction to this is minus 12 u squared, this integral. This r plus 2 permutations. Okay. So the minus sign came because here it's positive, but you're writing it as a coefficient of minus of an term, so that's why there's a minus sign. So this is our new u prime. And what about the leading term? Leading term had a correction like this. So the leading term, so let me call the leading term as u2. So I'll write the leading term as u2 times, q1. What have I called it? So let me put it this way: u2 of q1 with a half. So this is 0, so you can call it prime if you want. So this is 0 less than this, less than 1. Okay. I want to, my quadratic in sigma naught is a term of this type. This is the coefficient that I am trying to calculate. Okay. To begin with, your coefficient here, what was the starting coefficient here? Your starting value of u2 originally was equal to q squared plus r. This is how what it started out as. Okay, remember your term was q1 squared plus r sigma naught sigma minus 1. This is the starting. After the correction, you get some u2 which you have to evaluate. So it will be the sum of your original one plus this correction with all the rescaling. So this will be new u2 will be u2 original plus correction plus rescaling. Why rescaling? As I said, your original q after you remove half the momenta, this had a range to half, now it has a range 1 and you rescale all your variables. So let us evaluate this. So here is the expression. So your u2q I claim corrected, which you call it prime, is how many sigmas are there? There are 2. So you get a factor c squared when you put it in terms of primes. How many integrals are there? There is only one integral, and you are changing the range from half to 1. So you are replacing q1 equals q1 prime by 2 and making it range to 1. So you get a factor of 2 to the power of minus d. Okay. This is exactly what you had in the Gaussian model also. This is the rescaling factor. Times the first term is we had q1 squared plus r. That was your starting term. In terms of q1 prime, this is q1 prime squared by 4 plus r prime, because q1 is q1 prime by 2. Remember, we had this in the Gaussian model also, and then we chose this to get rid of that 4. Okay, that is what we did in the Gaussian model. But now there are corrections coming from this one. So we have to do this. This integral gives you the following thing. It's there's a factor of half. This is an overall. This is 6u is a thing, but if you factor out the half, because you want to factor out a so where is my expression for u? So I take out this half. I want to factor out a half. This 6 will become 12. Okay. So 12u times this integral. Where this p is ranges from 0 half less than p less than 1. Is this clear? So this is, I've just written this, instead of q3 I've called it p. That's no big deal. The range is exactly this, because that's the range of you're integrating. U is there, and this 6u I've written it as half times 12u, and this u2 comes with a factor of half. There's an overall half here. Where is my u2? Our action is half u2. Where did I think I wrote? This half. Okay, so I took out a half, put this as 12 times u. So this is my u2. In principle, this could have been a function of the momentum q1. This term is a function of momentum, but this term is not. Okay, so this is a function of q1, independent of. So your corrections in general can depend on the momentum of the sigma naught, and it need not. Okay. So all that remains to be done is to actually do these integrals, and here we are going to make some approximations. So I hope everything is, if there is any doubt, this is a good time to stop about the combinatorics or any of the rescaling. So the non-trivial thing is to do the combinatorics right and do your rescaling correctly. So how are we going to do this integral? So you can call it that. We are going to, since this is close to 1, we will just approximate it by c times, okay, this approximation again for the same range of integration. So this is the p integral. So I just approximated the p by 1, okay. And actually I have written it as not c, but yeah, so I write it like this. Let me erase this and write this as 1 by 1 plus r times integral over 1 half less than p less than 1. So I said approximate p by 1, take it out, do this integral, and we will approximate this by c by 4. So c is basically 4 times this integral. The volume of that space with some normalization 4. Okay. I think this 4 is chosen because this answer becomes close to 1 or something. This is just notation, the way Wilson did it originally. But you see, there's an approximation here. This is just some number, but the r dependence we have correctly. It is 1 plus r. Okay. Similarly, we will approximate the second integral, this one. So we will write this as 1 by p squared plus r, 1 by q1 prime by 2 plus q2 prime by 2, sorry, by 2 plus p squared plus r. And again, this is in the range half to 1, this is in the range half to 1. So we will approximate it by 1 plus r squared, and then the same integral over p times 1. Okay. So that will also be c by 4 squared. Okay. So that gives, so putting everything together, you can see the correction to r prime is, so as we said, we use this, scale this and choose it equal to 4. So this is 4, so choose this equal to 4. So this will become 4r as before, exactly. So we choose so the first term is 4r, that's this, plus this correction. This correction is 3c u by, okay, 3 is for the 3 permutations. Since we have taken it, doesn't depend on the external momentum, they all contribute the same way. So it's just that. So 12 by 4 gave me 3. And then, well, sorry, the permutations were for the quartic term, not for this. So this is just 4 into 3 is 12. And then what else? U prime. So once you choose this, now let's see what this factor is. So c squared or zeta, this is zeta squared 2 to the power of minus d equals 4. So zeta is 2 to the power of 1 plus d by 2, 1 plus d by 2, right, 1 plus d by 2. Okay. So you put this in here, so that gives you 2 to the power of 4 times this 4 plus 2d minus 3d. This thing is equal to that. Okay. So this is 2 to the power of 4 minus d. Okay. So what multiplies the u prime is 2 to the power of 4 minus d. Because I haven't specified d. Okay. And then you will get u minus what did we calculate? That integral. So I'll just write down the answer. You can check if it's 2. 3 times c by u squared into 1 plus r squared into 3. These are the 3 permutations. So yeah, this 12 times c by 4 gave me 3c, and this is a 3 permutations. It was 36 and we wrote it as 12 and 3, but in this approximation nothing depends on the momentum, so all the permutations give you the same thing, so that's why 3. Okay. So this is the final recursion. Is this clear? As you can see, it's analytic. There's no non-analyticity anywhere because we're always dealing with a finite blocking. So what we have to do now is to study this recursion. So let me erase all this. So remember, what is the procedure? We've got a recursion by this procedure of blocking or removing half the degrees of freedom. So you start with some r naught u naught, which is starting point, block to get r1 u1 using that. Keep doing that till you do it, say L times. Keep doing this. Each time you repeat that. So your recursion relation is simply r L plus 1 is 4 times R L plus 3C U L by 1 plus R L, and U L plus 1 is 2 to the power of 4 minus D U L minus 9C U L squared by 1 plus R L squared. Okay. So that's your recursion relation. Notice that when u is 0, this is not there, this is not there, and you just get R L plus 1 is 4 R L, which is what we got for the Gaussian model. Okay. So this is a modification of that. What about so after L's recursions, if your lattice spacing initially was L naught, here it's 2 to the power of L times L naught. So your effective lattice size now is that much, and our idea was to keep doing this till you reach the correlation length. Okay. So your initial correlation length is c in lattice units. It will become c by 2, and then you keep going c by 4 until finally it will become about a 1. That point you can stop. If c is infinite, you can keep going the infinite number of times. So as I said, what's going to happen when you do this an infinite number of times? Typically, if you have an interesting theory, it will go towards some fixed point. Okay, at the fixed point, for the Gaussian fixed point, remember what was the fixed point? We found that the fixed point is where the recursion gives you back the same answer. So if you had just r prime if you just had r prime equals 4r, the only possibility was 0 and infinity. Okay, so 0 or infinity in the Gaussian model. Infinity is not interesting. If it's infinite, that means there are no fluctuations at all. It's infinitely damped. It's in field theory language. It's infinitely heavy field. So what is interesting is 0 where the correlation length is infinite. So this is C equals infinite. This is C equals 0. So this is not interesting. This is the interesting one. Here there are more non-trivial solutions possible, and that's what we have to investigate. Okay. So we expect find a fixed point R equals R star, U equals U star, such that this recursion, so you take it solves that means R L plus 1 equals R L equals R star, U L plus 1 equals U L equals U star. You have to solve that. And it might happen that your solution happens at when U is a very large number. Okay. If that happens, then you're not within perturbation theory because you want a solution where U is small. This whole procedure depends on U being small. So the question is, can you find a fixed point in a regime where your calculation is reliable? Okay. And that is why Wilson found this clever trick. He said that if you choose this quantity to be small, some epsilon, you will find such a solution, and that solution will have a U which is of order epsilon. Okay. And if epsilon is small enough, then this procedure is reliable. Of course, you might say, what is the meaning of 4 minus epsilon dimensions? But that's a mathematical, just a mathematical question. There's no physical meaning to that. It's just a mathematical procedure for doing this. So the statement is you do it in 4 minus epsilon dimensions, and you get a non-trivial fixed point. And then once you study that fixed point, you might try to extrapolate epsilon to some value which is interesting, like 1, because you're interested in 3 space dimensions and epsilon is 1, and you might ask whether these answers are reliable. So he did what is called an expansion in powers of epsilon. Okay. And then in the end he put epsilon equal to 1, so it's like a series expansion assuming it converges. It may be good in regions where it's order 1, and then he got some well-defined results which agreed with experiment. Okay. So that is his famous epsilon expansion. So what we're going to do is we're going to solve this and see what the fixed points are. Okay. I should point out that if well, let's solve the fixed point experiments. So we have to solve this equation. U equals 2 to the power of 4 minus d times U minus 9c U squared by. So I put U on both sides. And now you'll see the role of this epsilon. So if you bring this to this side, you will get U times 2 to the power of 4 minus d minus 1 equals 2 to the power of 4 minus d times 9c U squared by 1 plus R squared. So I've multiplied the whole thing by a minus sign. So it's 2 to the power of 4 minus d minus 1 is this. So there's U here and U squared there. Of course, U equals 0 is a solution, we know that. That's the Gaussian theory, but we are not interested in that. So we cancel out U on the side and remove that U. 2 to the power of 4 minus d, 2 to the power of, that's 2 to the power of epsilon. So we'll write this as 1 e to the power of epsilon log 2. So this is 1 plus epsilon log 2, small for small epsilon. So what is this? So this is, or you can solve for this. So U equals 2 to the power of 4 minus d minus 1 times 1 plus r squared by 9c. Okay. So let me, this is the solution for u. Let's solve for r. So the equation for r is r prime is 4r okay, and we set r prime equal to r, so equal to r. So what do you get? You get 3r plus 12 cu by 1 plus r equals 0. So now this is giving you a non-zero value of r. It's of order u. Okay. So if you assume that u is small, r is small, we can neglect this. So neglect this if r is small, and you get a solution that says r is minus 4 cu. So the fixed point is r star is minus 4 u star, assuming r star is a small number, assuming u star is a small number. So this is a solution for u star. So everywhere you can put, okay, and if you neglect r star, this is just equal to epsilon log 2 by 9c. So neglect, if you suppose r star is very small, you can neglect it here, then this is a fixed point. So you see it's of order epsilon. So you can choose epsilon to be arbitrarily small, so that this perturbation theory makes good sense, and you get a solution, you get a non-trivial fixed point, which is very interesting. Okay. So the fixed point is, so let me summarize, u star is epsilon log 2 by 9c, and if you plug this there, r star is minus 4 by 9 . So I'll stop here. So this is your fixed point. Okay. So what we're going to do tomorrow is to analyze the properties of this fixed point, and what happens if you're slightly away and you're right on the fixed point, slightly away from the fixed point, etc., how the couplings flow, etc. So we'll do that next time.